You've been waiting for this one, haven't you? Welcome to Curiosity. Today we'll discuss quantum physics and its implications for our free will. But before I start, let me tell you that there are a lot of events in quantum physics that I so want to discuss, but I won't be able to in this video so as to make it as small as possible. But you can still see that it's quite long. I'll possibly discuss all those events in some future videos after the free will series. Anyway, let's start. So what is quantum physics? Simply put, quantum physics is the study of the microscopic world, the physics of the minute atoms and subatomic particles, the very building blocks of the universe. And if you don't know already, the quantum world is flabbergasting. Particles popping in and out of existence, one particle being at many places at the same time. Wave-particle duality, quantum tunneling, quantum superposition, quantum entanglement, quantum decoherence, quantum Darwinism, and many other astounding phenomena. Studying quantum mechanics could bring us closer to knowing the true nature of reality. If Newton's and Einstein's physics is based on the assumption that the universe is deterministic, in which the universe is pre-decided and predictable, quantum physics is based on the assumption that the universe is probabilistic and events take place randomly, which is completely opposite to the causal deterministic universe that we have been talking about in all these videos. The quantum world is a completely strange world altogether. This is an electron, it's a quantum particle, and it's exactly here, but it's also here and here at the same time. Wait, what? That can't be true, right? Yes, it's like... No, well, actually, we don't know where the electron exactly is. Instead, we only know where the electron might be. It's kind of like until we measure it, it's at many places at the same time. But actually, it's like there's no notion of an electron having a position before measurement. It's very likely to be somewhere here and much less likely to be out here. But how can we not know where the electron is? I mean, there has to be something wrong with this theory, right? Quantum physics is weird. In classical physics, you can exactly predict how something behaves, but that's not the case for quantum particles. Quantum physics doesn't tell us what exactly is going to happen. It only tells us that if you were to look at the electron, most likely you will find it right here. It is probabilistic. Okay, but what does that mean? Let's start with the central mystery of quantum mechanics. Young's double-slit experiment. Let's take a source of monochromatic light shining against a screen with two slits extremely close to each other, with distance between them lesser than the wavelength of light we are using. The light is coming out in waves like ripples in a pond. As the light hits the screen, it goes through the two slits, and each slit becomes like a new source of light waves, and the light spreads out again. It diffracts, and as the waves of light overlap, they interfere with each other such that where a crest hits a trough, they will cancel out. Where a crest hits a crest, they will amplify, and where a trough hits a trough, they amplify. On the back screen, you end up with what's called an interference pattern, a series of light and dark fringes where the waves have either cancelled out or worked together in phase. Imagine doing the same experiment again, but this time with electrons. So imagine we have an electron gun which fires a stream of electrons. Let's block off one of the two slits. You'll see a lot of electrons hitting the second screen. A lot of electrons will be blocked by the first screen. They won't go through that slit. A lot of electrons are going clean through the slits. Some are sort of bouncing off of the edges of the slit, and they're kind of being deflected a bit, which is why you get a bit of a scatter. The first mystery of quantum mechanics comes when you open the second slit. When we open the second slit, we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the electrons have gone through the two slits, it's as though the electrons have gone through the slits behaving like waves, and you get interference of the waves and you get this pattern. Unbelievable. Now, you could try and say, well, maybe electrons behave in a very strange way and only a certain number of them are allowed to clump together in a certain way due to charge or gravity or other forces or something. Electrons saying, me and my gang, we're going to form a band there. You guys go and make a band next to us but not touching us, maintain a distance. There could be some forces between atoms that make them coordinate their actions in a way to give this pattern. If that's really the case, let's not try to force the issue and get this sorted. Let's not send the electrons all through at once, but send them through one at a time. Leave enough of a time gap for the electrons to get through to hit the screen. Some electrons will hit the first screen and not get through, but those that do get through will hit the back screen. Let's send them through one at a time. So let's run the experiment again, slowly. That is one electron at a time, temporarily separated, and gradually you will see as the electrons go through, they will look like they're just randomly arriving in the other side. You keep sending them through one at a time and gradually that same pattern appears, as if to show that the electrons are actually behaving like waves. So each electron by itself is somehow contributing its small part to the overall resulting wave-like behavior that we see in the interference pattern. How does it do it? Now, we can try and be even cleverer. What if we were to spy on the electron and see where it goes? We're going to detect which slit the electron goes through. So you put a detector just adjacent to one slit that will flash or beep whenever it sees an electron go through that slit. Fire the electrons through one at a time. Around 50% of the time, the detector will beep. The other 50% of the time, it doesn't, meaning that the electron has gone through the other slit. We can see that two stripes are formed on the screen corresponding to the two slits, meaning the electrons moved through those slits. But that's a completely different result to the interference pattern we saw earlier. How could that be? How could electrons behave that way? Now, let's just try one last tweak in the experiment. Leave the detector right there, but just unplug it so it doesn't actually work, but just stays right there. Don't let the electrons know that you're not spying on them. Make them think that you're still detecting them. Okay, listen up electrons, we're gonna run the experiment again. Okay, get ready, we're going to be checking on you, alright? Let's run the experiment again. Now see the results. The interference pattern again. It's as if the act of actually detecting or measuring the electron changes its behavior. Detecting the electron makes it behave like a particle, and until detected, it behaves like a wave. Absolutely mind-blowing. Okay, so now you're saying that electrons are waves, but how can a particle be a wave? Well, no, they're not actual waves. It's just that at these super small scales, when not measured, the existence of particles, atoms, and even big molecules is not tied to just one point in space. In quantum mechanics, particles don't have definite properties until measured. Rather, they are described by something called the wave function. In fact, a particle is its wave function. The wave function doesn't just consist of information about the probability of the location of the electron, but also everything else about the electron, like its momentum, spin, and energy. We cannot directly see or measure the wave function. The wave function could only tell us about the probability of finding an electron at some point in space. Quantum particles really behave like this weird wave of probability. So even though the electron is a particle, its existence is controlled by a function that behaves like a wave. But whenever we detect an electron, we always see it as this localized particle at a particular spot. We call the mathematical description of this wave-like distribution of properties a wave function, and the equation that the quantum particles obey is called the Schrodinger equation. But what are these waves of or waves in? You can kind of consider that the probability of existence is waving. Now, what causes this transition between a wave of many possibilities and a well-defined thing at a particular spot? Now, this weird quantum behavior can be explained in a lot of ways. It could have a lot of interpretations. In fact, until now, nobody knows for certain which interpretation is correct. The answers aren't known yet, but the various interpretations of quantum mechanics do try. Let's talk about these interpretations. The first one. As of now, this is the most popular interpretation of quantum mechanics, but its popularity has decreased massively in the last few decades. The Copenhagen Interpretation. This is a view postulated by Werner Heisenberg and Niels Bohr, who pioneered quantum mechanics at the University of Copenhagen in the 1920s. The Copenhagen interpretation says that the wave function doesn't have a physical nature. Instead, it's a representation of pure possibility. It suggests that a particle exists only as a wave of possible locations that ultimately consists of all possible paths and properties. It's only when the particle is detected or measured that a location and the path it took to get there are decided. The Copenhagen interpretation calls this transition from a possibility space to a defined set of properties the collapse of the wave function, or the wave function collapse. It instantaneously shrinks from encompassing a huge range of possible measurement outcomes to encompassing only the outcome that was measured, and that value is selected randomly. Whatever causes this random selection is not the Schrodinger equation. It's something extra, and this interpretation doesn't explain why or when this really happens. It also violates the principle of conservation of quantum information. The Copenhagen interpretation explains the result of the double slit experiment by saying that the electron does not travel as a particle or a physical wave along one of these paths. Rather, it travels as an abstract probability wave, something we call a wave function. That probability wave defines the location of the electron at a point when you measure it. The Copenhagen interpretation states that prior to measurement, it's meaningless to talk about a real physical state for the electron. It exists only as the possible outcome of a future measurement. This property of quantum systems is called quantum superposition. A particle is in a superposition of different states until measured. So Copenhagen interpretation tells us that when we make that measurement, the wave function collapses. It goes from a cloud of possible final destinations for the electron to a definite spot on the detector screen. It's almost like the universe is allowing all possibilities to exist and holds off choosing which one becomes actual until measurement is made. In the Copenhagen interpretation, when the measurement is made, the final result on the screen is random. It's indeterminate. Nothing determines the exact position of the particle on the screen. It just randomly appears at a point on the screen. It is considered to be uncaused, unlike the causally determined universe that we have been talking about in all these videos. This is quantum randomness. The collapse selects one of those possibilities to become actual. This selection happens in a fundamentally random way. God does play dice with the universe after all, although the dice are weighted towards certain results. This is a completely non-deterministic interpretation of the universe, because there's no underlying predictability here. And if you thought that the Copenhagen interpretation is freaky, wait until you get to the many worlds interpretation. The many worlds interpretation says that the universal wave function is objectively real and that there is no wave function collapse. This implies that all possible outcomes of quantum measurements are physically realized in some world or universe. The evolution of reality as a whole is strictly deterministic. The many worlds interpretation is also called the relative state formulation, or the Everett interpretation after Hugh Everett, who proposed it in 1957. In the many worlds interpretation, the wave function never collapses and the universe just evolves deterministically. During the so-called measurement, the universe branches itself into its many parallel worlds and all outcomes manifest. The illusion of randomness is that we find ourselves in the one branch of the wave function corresponding to the reality that we perceive. But we aren't randomly placed in that branch, we just are a part of that branch. The subjective appearance of wave function collapse is explained by the mechanism of quantum decoherence. Copenhagen interpretation states that a quantum system is literally in a state of undefinedness until observed, at which point the wave function collapses into a defined state. All particles take on defined properties and one actual reality is chosen from the many possible ones. The Copenhagen Interpretation gives us a non-deterministic universe. The wave function evolves in a precise way, perfectly defined by the equations of quantum mechanics, but at the moment of measurement, a single reality is randomly selected from the distribution of possible realities. The dice are thrown when the wave function collapses. That collapse signifies the transition between the quantum and classical realms. In many worlds interpretation, all possible states of the quantum system continue to exist. It evolves forever by the Schrodinger equation. Rather than choosing one reality out of many, when we observe a quantum system, we sort of just become part of one of the realities and have no access to the others. The many worlds interpretation gives us a deterministic universe, or rather a deterministic multiverse, and implies that there are most likely an uncountable or infinite number of universes. Now, what is a measurement? For now, just think of a measurement as an interaction between quantum systems or particles in which information is transferred or leaks out or escapes out of a system of particles. When irreversible energy transfer occurs between systems of particles. So, a measurement collapses a superposition of states into a single state. One of the founders of quantum mechanics, Erwin Schrodinger, found the principle of superposition to be ridiculous, and he proposed his famous reductio ad absurdum Schrodinger's cat thought experiment to describe this absurdity. It goes like this. A cat is in a box with a flask of poison. A machine containing a radioactive element is set to shatter the flask as a consequence of the decay of the radioactive element. If or when that happens, the cat dies. That radioactive decay is a purely quantum process, and so, until it's observed, it exists in a superposition of states. It has both decayed and not decayed. But doesn't that mean that the entire macroscopic system attached to that quantum event is also in superposition? If so, the cat should be simultaneously alive and dead until we open the box. But why can't the cat collapse its own wave function? And from its point of view, is the physicist outside also a quantum blur until the box is opened? And what about the entire rest of the universe that's not currently being observed by physicists or cats? Interestingly, quantum superposition doesn't extend to macroscopic scales. It disappears when the macroscopic world emerges from the microscopic. This has come to be known as decoherence. When the wave functions describing quantum systems overlap sufficiently, in other words, they are coherent, it's possible to get inference in the double slit experiment. But when these systems interact with their environment, coherence is lost and parallel histories fall out of alignment. They can no longer interact with each other. The many worlds interpretation proposes that reality splits into different branches every time quantum states diverge into different possibilities. For example, at every particle interaction with information leakage everywhere in the universe. But it seems a bit ostentatious to propose uncountable, eternally branching universes just to get rid of this wave function collapse. But remember, the Copenhagen interpretation itself proposes multiple worlds in the superposition of parts or properties of a quantum system. Actually, many worlds appears to be the more pure interpretation of the mathematics of quantum mechanics, because there is nothing in that math that requires the collapse of the wave function. So many worlds is more economical in the parsimony it adds to quantum mechanics, but it is not particularly economical in the number of universes it predicts. Now, in many worlds, what happens to the rest of the wave function once measurement happens? In general wave mechanics, we say that a set of waves are coherent if they match in frequency and if the shapes of the waves are the same and if there's a constant phase difference between them. The peaks and troughs either line up exactly or have a constant phase offset. Laser light is an example of a coherent wave. Let's analyze what happens in the double slit experiment again. So imagine a single photon traveling to a single spot in the center of the screen. The probability of the photon having reached this particular spot is determined by the sum of all possible trajectories to that spot. In this case, that mostly means these two paths, these wave function slices. which can be represented with simple sine waves. Because the path lengths are the same, the peaks of one wave line up with the peaks of the other. The two waves are perfectly in phase with each other. We call this constructive interference. Because the wave function is amplified at that spot, there's a high probability of the particle landing there. Now, just a little left of center, these two possible paths to that spot have different lengths. Here the peaks of one wave line up with the troughs of the other, and the wave function completely cancels out. That's destructive interference, and the probability of the particle ending up there goes to 0. And as we continue to the left, we find a new location where the peaks line up again. Here the path lengths differ by exactly one full wave cycle, and so on. So we ultimately see this series of bands, lots of particles where the wave function is amplified, only some where it's cancelled. We can see this interference pattern if there is coherence between different parts of the wave function. The key in this experiment is that all photons exit the slits with the same phase relationship. In this case, the phases match perfectly when the wave function leaves the slits. Peaks and troughs come out at the same time. But it still works if they don't match exactly, as long as we get the same relative phase offset between the two slits for every subsequent photon. A constant phase offset will just shift the interference pattern to left or right on the screen. Now let's talk about decoherence, the point where we lose our ability to distinguish the multiple histories. To destroy coherence, all we need to do is to mess up that phase relation. For example, add a collection of particles to one of the slits. The part of the wave function corresponding to a possible path of the photon is now disturbed by those particles. We can think of that wave function slice as the possible photon being absorbed and re-emitted by those particles, and so the wave function leaving that slit acquires a random phase offset compared to the other slit. Technically, that emerging wave function can still interfere with itself. The random phase offset would just shift the pattern left or right for that photon. But that shift would then change for each subsequent photon. New photons land in unpredictable places. So in the end, we would just see a blur corresponding to overlapping patterns instead of a clean set of light and dark bands that we saw in coherence. The key here is that we lost information about the relative phase, and so we lost the ability to see interference patterns. We lost the ability to distinguish the effect of multiple histories. From our perspective, the wave function has lost coherence. Decoherence has occurred. This is exactly why any attempt to observe which slit the photon passes through destroys the interference pattern. A measurement device introduces some level of decoherence to the wave function before it reaches the screen. So now we have a basic understanding of coherence and decoherence. Let's now leave the slits alone and let the coherent photon wave function reach the detector screen. There, the photon energizes electrons in a pixel on the screen, which results in an electrical signal passing along wires to a computer and eventually into our brain. We can think about the photon wave function becoming mixed with the wave functions of the quantum particles along this chain. We can imagine separate possible histories continue across the screen, and superpositions of signals traveling from those pixels ultimately travel to the brain of the observer. But by now, that wave function is getting pretty messy. Phase differences get introduced between the different branches of the increasingly complex wave function. Phase offset becomes less and less knowable the further the wave function advances. Without a consistent phase offset, it's not possible to map an interference pattern. The once coherent particles with their superposition of both separate histories that could merge become decoherent. Ultimately, that expanding wave function includes the circuitry of the computer and then the circuitry of your brain. By this time, as far as you're concerned, the wave function has collapsed. But actually, the original double-slit wave function may well continue to expand and complexify as it mixes with the wave function of the rest of the universe. But there's no way for you to see its other branches. Those have decohered from your branch. So long story short, the wave function splits after it passes through the slits and interacts with itself. The wave function ripples through the detector, along the wires, through the computer circuitry, as photons from the screen, as action potentials through our optical nerves, and eventually as signals firing in the neurons in our brains. And then it manifests as conscious awareness of a dot on the screen. The Copenhagen Interpretation says that at some point in this process, most of the wave function vanishes. The paths to the electron's wave function not corresponding to our observation of that spot cease to exist. Many worlds says that the wave function persists. It says that waves representing every possible location on the screen travel down the same wires through the same circuitry into the same brain. They still overlap, stack on top of each other, but they no longer interfere, neither constructively nor destructively. That's because the many interactions that these wave function branches experience on their way to your brain render them forever inaccessible to each other. Decoherence has occurred. Once decohered, these worlds overlap and move through each other, but they can't add together in meaningful ways. Once there is no longer a recoverable phase relation between the branches of the wave function, the worlds have separated forever. That means the wave function of your brain also has branches, different internal superposed states corresponding to different worlds of the many worlds. But those parts of your brain wave function are out of phase with each other. They match in many ways, including physical location, but there are subtle phase differences. On one branch, a collection of neurons fire to observe a spot here. On another branch, a different set of neurons fire, leading to the mental experience of a different spot here. Okay, so different yous have observed all results. In one version, suppose you move left, in the other, you move right. But where are these worlds? Right here. Just that I am out of phase with the other eyes of the other universes. They overlap in location, but are so out of phase with each other that they can never interfere with each other. They just pass straight through. So both mental experiences exist simultaneously, but you only experience one because you are that particular mental experience, and you just experience it. You don't freely affect the laws of quantum physics by any means to, say, collapse the wave function of a particle to your desired location. This decoherence is an increasingly accepted explanation of how splitting of the many worlds occurs and the apparent collapse of the wave function in Copenhagen, and thereby the shift from the microscopic to the macroscopic world. In fact, there are even more profound explanations of how the shift from the quantum world to the classical world happens, which involves quantum entanglement and quantum Darwinism, but I'm not gonna discuss that in detail here. No, I just have to. Just a little bit. Quantum entanglement, or Einstein's spooky action at a distance, is the phenomenon in which two or more particles link up in a certain way. No matter how far apart they are in space, their states remain linked so as to abide by the conservation laws, say conservation of angular momentum. That means they share a common unified wave function. Until measured, their wave functions are entangled and they are in a combined superposition of states. So measurement of one of the particles can automatically provide information about the other entangled particle regardless of the distance between them, even if they are billions of light years apart or at the opposite ends of the universe. And any measurement of one of the particles will determine the state of all the other particles in the entangled system. The combined wave function supposedly collapses and it sows the seed for the macro world. The transition towards the macro world occurs because most quantum interactions depend heavily on the relative location of interacting particles. Therefore, information about relative particle locations is robustly shared and propagated through the entanglement network. The individual particles do not have well-defined locations. They stay quantum weird. But the entanglement network has this sort of collective consensus about those locations. The structure of macroscopic objects, including Schrodinger cats, are strongly defined by the relative positions of their particles. Therefore, the states of cats and dials will always appear well defined. If you haven't noticed already, I've just now probably explained how reality works. If you could somehow put a dust grain in the air in a quantum superposition of states, you can calculate that it would decohere in this room in about 10 to the minus 31 seconds. That dust grain, even in vacuum with its interactions with thermal radiation, infrared photons from the warmth of the room, would still cause it to decohere in about 10 to the minus 18 seconds. Even if you put that grain of dust in the cold emptiness of interstellar space, it would still decohere in about a second because of the microwave photons out there from the cosmic microwave background radiation. So, in other words, the reason we can't generally observe quantum effects like superposition in objects of everyday scale is not because there's some law of nature that forbids quantumness at those scales, but because decoherence will destroy it almost instantly. Why don't I see an interference pattern when suppose I throw apples through two slits and don't watch which door they go through? Because even if I'm not watching, plenty of other things are interactions in which irreversible energy transfer happens occur. The apple will interact with air and light and they collapse the wave function for me. So quantum superpositions are rare because they are so fragile. Nevertheless, quantum decoherence and quantum entanglement do not solve the measurement problem, which is the most fundamental problem in the field of quantum mechanics, the de Broglie-Bohm pilot wave theory. There is one interpretation of quantum mechanics that somehow manages to skip the wildly extravagant notions like the superposition principle of the mainstream interpretations of quantum mechanics. It avoids most of the counterintuitive consequences of the orthodox versions of quantum mechanics, and it retains a closer to classical picture of physics. It's the de Broglie-Bohm pilot wave theory, also known as Bohmian mechanics. It is probably the most solidly physical and intuitive interpretation of quantum mechanics. Louis de Broglie's theory reasoned that there was no need for quantum particles to transition in a mystical way between non-physical waves and physical particles. Why not let's just have real waves that push around real particles? In Bohmian mechanics, the wave function describes a real wave of some stuff that we don't know yet. This wave guides the motion of a real point-like particle that has a definite location at all times. They're just being guided by the wave function. Importantly, the wave function in pilot wave theory evolves exactly according to the Schrodinger equation. This means that pilot wave theory makes the same basic predictions as any other interpretation. For example, this guiding wave does all the usual wavy stuff like form an interference pattern when it passes through a pair of slits. The interference pattern occurs because particles follow the paths sketched out by the wave. The wave defines a set of possible trajectories and the particle takes one of those trajectories. But the choice of the path isn't random. If you know the exact particle position and velocity at any point and all the forces acting on it, you could figure out its entire future trajectory. That makes pilot wave theory deterministic. Apparent randomness arises because we can't ever have perfect knowledge of initial position, velocity, or other properties of a particle. In the double slit experiment, for example, Bohmian mechanics explains this by saying you don't actually know exactly where the particles started out. The first particle might have been just left of the previous one, which means they end up going to different places. It's just because you don't know exactly where it started that you don't know where it will end up. If you knew the hidden variables, you could predict the outcome of a measurement. But the variables are hidden, so you can only calculate the probability of getting a particular outcome, just like the earlier two interpretations. So the uncertainty in this scenario is due to our inability to measure the particle's initial state, not because the particle's position is inherently unknowable. Nowadays, the popularity of Bohmian mechanics is on the rise, but this theory does have some flaws of its own. It needs a wee bit of extra math that other interpretations don't, and in addition to the Schrodinger equation that instructs the wave function how to change, it also has a guiding equation that tells the particle how to move within that wave function. That extra math is considered unparsimonious by some physicists, but the Bohmian team says the guiding equation is derived directly from the wave function, and that's not a strong point against this interpretation. A bigger problem is that it contains real complexity that is not encoded in the wave function. It's the so-called hidden variables, details about the state of the particle that are not described by the wave function. Einstein loved the hidden variables theory. According to pilot wave theory, the wave function just describes the possible distribution of those variables given our lack of perfect knowledge about the particle's properties. Now, one might say that Bell's inequality rules out hidden variables in quantum mechanics, but it can only rule out local hidden variables. Pilot wave theory is a non-local hidden variable theory. Its hidden variables are global, and it's compatible especially with quantum entanglement. Okay, so what do you mean by non-local hidden variable? Something is non-local when you have a particle over here that affects a particle over there instantly. A particle's properties need not necessarily be at that particle. It could extend to all of space. A universal wave function is spread all across space. In other words, these variables are distributed throughout the entire universe, not just at the particle. So pilot wave theory cannot be ruled out based on Bell's inequality. The great thing about Bohmian mechanics is that there is no wave function collapse and hence no measurement problem. But since pilot wave theory is a non-local theory, it has become very difficult to get a quantum field theory out of it. Many have made attempts, but there's simply no pilot wave alternative for standard model of quantum physics right now. The other interpretations of quantum mechanics are compatible with quantum field theory, which is the relativistic version of quantum mechanics and one of the most successful theories in science. Quantum field theory pretty explicitly requires that all possible particle trajectories be considered equally real. It is consistent with the principle of quantum superposition, but pilot wave theory is not. Pilot wave theory also does not account for Einstein's relativity. Remember, we discussed relativity in this video of the free will series. That means it's definitely an incomplete interpretation of quantum mechanics. But do you know what's crazy about physics? None of these interpretations can account for gravity. None of them have that sorted out. The one that combines quantum mechanics and gravity. Now, there are a bunch of other interpretations as well, which I'm not going to be discussing in detail today. Penrose's interpretation, in which gravity collapses the wave function. Von Neumann-Wigner interpretation, in which consciousness collapses the wave function. But it has been experimentally proven that consciousness is not needed for wave function collapse. Spontaneous collapse interpretation, in which collapse of the wave function is a property of the particle, but it happens very, very rarely, maybe once in millions of years. But the collapse of just one particle is enough to collapse the whole system due to quantum entanglement. Then there is transaction interpretation, in which there's kind of a time travel transaction of information between future wave function and past wave function. No interpretation of Richard Feynman, in which he says, "Stop asking questions, shut up and calculate." Cubism, relational interpretation, and many more interpretations which I'm not going to be discussing today. For now, let's just stick to free will. Each of these interpretations is either deterministic or random. Alright, even if we grant, although unlikely, that the deterministic interpretations of physics are all wrong, we could only get to the conclusion that the universe is fundamentally random, and randomness by definition is uncaused and uncontrolled. You don't have control over randomness. It happens out of nowhere. When determinism makes your will unfree and forced by causes uncontrolled, randomness or indeterminism might sound free, but it won't be your will. It would be random. You will have no control over that will, that randomness. Your will is either determined, in which case it's not free, or it's not determined, in which case it's not a will. Free will is impossible. Suppose a mad scientist has captured your friend and implanted some kind of brain control device. He enters commands into a machine and your friend has no choice but to follow them. Most of us would say that he doesn't have free will, as someone else is now controlling all his actions. But what if the scientist got a bit lazy and decided to put the machine on autopilot and have a roulette wheel decide his behavior. With this addition of randomness, does he now have free will? Most of us would still say no, right? MIT physicist Max Tegmark did a detailed analysis and concluded that the brain is too wet and warm and macroscopic and prolonged for delicate quantum effects. Superposition of quantum states is notoriously difficult to maintain. As far as we know, for things that are warm, big and slow as us, the Newtonian laws are the effective physics. It requires isolation such that the system does not interact with other atoms or any other classical materials such as the various fluids and structures in the brain, because the quantum system would then become entangled with its environment and decohere so that it would no longer be in superposition. Tegmark showed mathematically that any superposed state in neurons would decohere within 10 to the minus 13 seconds. So such fast quantum mechanical effects influencing brain functioning is hard to imagine. Matthew Fisher, physicist at University of California, Santa Barbara, also showed mathematically that the temperatures needed to maintain superposition based on the frequency of neuronal firing is about 10 to the minus 7 Kelvin, which is of course much lower than body temperature of about 310 Kelvin or 98.6 degrees Fahrenheit. So the brain appears to be both too wet and too warm for quantum processing, just as Max Tegmark said. The human brain consists of a completely different environment that is not conducive to quantum particles for their random behavior to affect brain processes. For significant quantum effects to manifest themselves, you need to be in a very controlled environment, preferably at an exceedingly low temperature, to screen out all of the noisy influences from the surrounding world. But the brain is actually anything but that sort of a system. Quantum effects on a large scale manifest only at very, very low temperatures near absolute zero. Brain is a hot, wet, noisy system. It's really hard to see how quantum mechanics could play a role for anything bigger than a tiny bunch of molecules. On a multicellular scale, it seems almost impossible to imagine that it would play a significant effect. In the presence of heat, atoms, molecules and tissues begin to vibrate, which makes the interactions between the waves very chaotic and lose its quantum nature. All the relationships between the different waves are scrambled up. That makes it very hard to see how quantum effects could exert any sort of serious impact in the brain. Those quantum effects are going to have to bubble up 20-30 orders of magnitude to begin to explain a single action potential, which takes about 3 or 4 milliseconds. That is about 10 to the 23rd times longer in duration than a quantum effect in an electron. That's a hell of a lot of bubbling up that needs to happen to get to just that level of biology, which just does not happen. There is an actual fallacy of composition there, that the features of the whole system have to be the same as the features of which the system is composed. The fallacy says that if the features that compose the system are random, then the whole system must be random. That does not follow. Just like the classical world, the quantum world too is still following the laws of nature. The law here being the Schrodinger equation or the Heisenberg equation. It's still a set of equations. Initial condition wave function, put it in the equation, out comes the other side, the prediction of what will happen. In the equations there is some probabilistic element, but the fundamental elements are not probabilistic. Just look at the mathematical expression of the laws of motion of quantum systems. Those equations are deterministic. They don't explicitly have any stochastic or probabilistic feature in them. There is a completely deterministic flow of the quantum state of quantum systems in space-time, and then the probabilistic element comes when one performs a measurement of one of these properties. So there's the laws of motion that are deterministic, and the outcomes of the measurements are stochastic. Some people say quantum physics has a mystery at its heart. Free will and consciousness are mysterious, so maybe one mystery explains the other. That doesn't really follow. That's fallacious thinking. It's a slippery slope and opens the window for all kinds of woo-woo and a bunch of charlatans like Deepak Chopra. But let's dive deep into quantum randomness. One important principle of quantum mechanics is the Heisenberg's uncertainty principle, which says that we cannot simultaneously measure the position and momentum of a particle. The more certain you are of a particle's momentum, the less certain you are of its position, and vice versa. Also, take superposition principle, a particle not being in a specific state at a time before measurement. But there are problems with the interpretation of this scientific conclusion. Even if in principle we cannot measure them, it doesn't mean that there is no definite position of a particle. Even if you do not know or cannot know the position and momentum of a particle before measurement, it does not mean that the particle doesn't have a position and velocity before measurement. Philosophers would say it's putting the epistemic cart before the metaphysical horse. It's also called the metaphysical horse fallacy. Metaphysics or ontology is the study of what is, what exists, while epistemology is the study of what we can know and how we know what we know. Is the result of quantum mechanics epistemological, or is it ontological or metaphysical? So is it the case that we simply do not know the properties of a particle before measurement? Or is it the case that the universe is fundamentally random at bottom? The Copenhagen Interpretation says that the uncertainty is ontological. It asserts that there's no such thing as a definite property of a particle before measurement. The metaphysical horse fallacy occurs when one takes as primary epistemology over metaphysics. Many facts about the world are generally considered not dependent on whether we can know about it and how we can describe it. And therefore, simply drawing some conclusions about what we can't know doesn't mean that it doesn't exist. So for example, if we can't know anything about a point of time in the past, doesn't mean that there isn't some fact of the matter about that point of time in the past. It just means that we can't know about it. Similarly, just because we can't know about the properties of a particle before measurement doesn't mean that that particle does not have any property before measurement. Trying to claim that our epistemology defines the metaphysics of the world is putting the epistemic cart before the metaphysical horse, the metaphysical horse fallacy. This doesn't prove determinism by any means, but it doesn't prove that the world is fundamentally random either. Quantum mechanics does not help us with saving us free will. Our neurons, brains with which our decisions are made, operate in the macro world where quantum effects are inapplicable and ineffective. Now, even if indeterminacy or randomness proves free will, this randomness is a property of all matter, not just conscious matter. Then why does it mean that only adult humans have free will and animals don't have it, or a tree doesn't have it, or a baby doesn't have it, or a rock doesn't have it? A decision is uncaused if it happens as a matter of pure luck or unluck. It just means that you did not cause those decisions. They just popped up uncaused, randomly, uncontrollably. If your decisions have reasons behind them, then they were caused by the principle of cause and effect, in which case you don't have free will. If your decisions do not have any reasons or causes behind them, then they just happened randomly. You did not cause those decisions. You don't know what came over you. They just came out of nowhere, in which case you don't have free will either. Remember the last video we talked about chaos theory and weather. Weather appears unpredictable for us with our limited ability and knowledge, but is it uncaused? No. Similarly, through experiments, quantum mechanics does appear unpredictable and random, but why do we have to conclude that it is ultimately uncaused? Even if we think it is locally random, there are reasons to believe in some kind of non-locality, and globally, the universe could be deterministic. You cannot conclude that the quantum world is random, as it could be that there are hidden variables at play. By the way, there are many prominent scientists and physicists who think the universe is ultimately deterministic. Now, even if the particles in the micro world did behave randomly and they somehow caused our behavior, that's still causality. You can't break away from the causal web. Even if everything was random, where is the free will? Quantum randomness negates free will just as much or even more than causality or determinism. If random events happen at the quantum level, we did not choose the randomness. You are not the author of the randomness. The randomness is not up to you. They are not influenced by you, regardless of exactly what you mean by you, because they are not influenced by anything. That's the whole point of saying they are fundamentally random. Nothing determines their outcome. There is no will in this, not yours and not anybody else's. The idea that we have free will, which gives us the possibility to freely select among different futures, is both logically incoherent and inconsistent with the laws of nature. The universe is either deterministic and we don't have free will, or it is indeterministic and we don't have free will, or it is some kind of weird combination of both and we just don't have free will. I appreciate it if you've endured all this and made it this far. Special thanks. Oh, my head hurts. Thank you all for watching the video. Subscribe to the channel. Please drop in your comments, like and share the video. And please stay tuned and stay curious. I'll see you in a bit.